afternoon, Armadacon. And here we have the first proper panel of Sunday afternoon. A minor tiptoe route through quantum theory by Martin Lavelle.
So, I guess in a way, the good thing about giving a talk about quantum theory is that we've all seen videos of people going, I don't understand quantum mechanics, and I'm supposed to be an expert in it. Nobody does. So I don't have to make you come out of the room thinking that you understand it. I do have to try to make you come out of the room thinking it was at least somewhat interesting. So let's see how we get on. I'm a more or less a former theoretical physicist at the university. I've done quantum field theory calculations for most of my professional life. And it works, as they say. You know, quantum theory is really successful. And you know, the Physics Nobel Prize, as your committee obviously recognized was going to happen, was awarded for quantum mechanics this year, some time after I was asked to talk about the subject. So they knew what was happening. Indeed. It's used in technology. I will give you a very slight hint of that, but I am a total theorist. I can just about change a light bulb. So I'm not going to talk much about technology. And it successfully predicts basic science results. And the thing that's really weird is the philosophical stuff. And I am not a philosopher, but I can at least try to indicate what sort of things confuse the hell out of people. So quantum mechanics is useful for lots of science and technology, and you can use things that Gary knows about, like scanning tunneling electron microscopes, to move individual atoms into place. This is a product placement. Other computing companies are available, and they are, I have it written at the bottom, and it's not being shown at the moment, which is a bit annoying. So let me go back to full screen view, so you can see it, because it will say what it is. Xenon atoms on a nickel substrate. So I think I'm actually going to show you the full screen, and I'm going to be horrible and move the slides from one to the other in a really bad way, because the page down button does that. I wouldn't call a full page. So, you know, if you look at somewhere like CERN, you know, we've all seen these pictures before in Gary's talks in previous years. You know, if you go to somewhere like CERN, it's all using quantum theory, quantum field theory, and again, it all works. It actually works really boringly. That's a subject for another talk, but you know, it would be really nice if they could actually tell us something from CERN that didn't make sense with the standard model of particle physics, because you know, I'm a theorist, but you know, theorists need clues from experiment. So you know, all of these sorts of things, lines, you've seen pictures, and so on, they're all interpreted using mathematics and quantum field theory.
Yes.
Okay, so let's try and talk about, a little bit about the source of the big confusion. And we'll go back to what people thought they understood about 125 years ago, roughly. So light, I mean, Newton said it was made of particles, but people had worked out, no, that's wrong. Light is made of waves. And matter, things like electrons, very recently understood at that time. Very, very recently understood. Matter, things like atoms, electrons, that's made of particles. You know what particles are. A particle is something like that. You know, it's an object. So what happens is, sorry, I'm just going to do it that way. I've got too many pauses. Quantum mechanics, though, tells us that everything can be understood both in terms of waves and particles. And the wave bit is very, very weird. This is called wave-particle duality. I'll use a few fancy words occasionally, but yeah, it's just the idea of waves and particles. and it is very weird. Okay, so about 125 years ago, a little bit less, Max Planck was talking to his son. Max Planck, by the way, is one of the good guys. He got a Nobel Prize in physics. I think everybody with one exception that I mentioned by name in this talk got a Nobel Prize. And Max Planck was a really decent bloke as well. You know, everything, I've read a biography of him, and he really seemed a decent person. You know. So he said to his son, I may have done something as important as Newton. And, you know, and then looking back on it, he said, I had to get a theoretical explanation for this problem. I'm going to tell you what the problem is, no matter how high the cost was. And the cost was bringing in quantum theory, very, very, very tentatively at the beginning, of course. But in the meantime, they claim that about a quarter, this is a few years old, I'm sure there's a more recent one which is higher, that about a quarter of the US GNP is based on quantum technologies. And again, the first of these quotes, and I think the only one I'm going to use, is from Planck. And if anyone can say they can think about quantum problems without getting dizzy, it only shows they've not been listening. Or it was badly explained. So what was the problem? Well, here is a light bulb, one of these incandescent light bulbs, you know, around at a similar sort of time. And you put a current through it, and it heats up and emits. But we've also all seen Predator, and some of us even have ducks with Predator on them. and Predator, you know, can see in the dark. You know, you can see the light, the infrared light, the infrared radiation that we're emitting. So we're all emitting, aren't we? You know, everybody in this audience has seen that in sci-fi films. So you have a classical theory which describes how that's going to be. And it says, okay, this is the frequency. So low frequency is things like the infrared. High frequency would be things more like blue or gamma rays and so on. And the classical theory predicts this red curve. Intensity is how much of it you're getting out. So, okay. Now this is not just about light bulbs, it's also about you and me. It's about that cup of coffee that you need in the morning. It's radiating off gamma rays straight into you. We need help from a nuclear expert on this one, I think. So classical theory was worked out in 1900. You can see, by the way, from the dates, this was all really fast. So Planck happened to know an experimentalist whose name I've forgotten, who was also working in Berlin and had got the best data. So Planck got this really good data, and he was able to find an equation using the sorts of functions that physicists like, and it really fitted the data perfectly. But where does that equation come from? I mean, you know, finding an equation that fits the curve is not everything. So Max Planck, this is him much older, he had his moment of desperation. He did something weird. He said, okay, what I'm going to say is that energy is only, so by our light bulb or by your body, yourself now, is only emitted in lumps. And we have this fancy Greek word, quanta, to describe that, but basically it just means lumps. And how big are these lumps? So you have to bring in a constant that describes the size. You know, just like there's the size of how the gauge of a railway. Well, there's the size of these things. It's called H. I don't know why he called it H. Everybody calls it Planck's constant. And it sets the size of the quantum world, and it's really, really small. Okay, so it's really, really tiny, which is why we don't notice these things in real life. If you're interested, there's a book by George Gamow called Mr. Tompkins in Wonderland, and that is about somebody who has these sort of weird adventures where he goes into a world where this constant is big. But yes, that's fun to read. Anyway, and this thing works. It gave the equation. So, but it's a weird thing. You know, why things only emitted in lumps? You know, nobody knows. So where does it come from? And what's it mean for the rest of physics? And that was where it stayed for a few years. Just by the way, to back up this thing, jumping into more or less the present, NASA's Cosmic Background Explorer, they took a view of the universe, the full sky, seen in infrared light, and then you chop out the dust from our solar system and other bits and bobs, and then you say, okay, can I fit this curve to Planck's equation, how much light there is for different frequencies, and that's it, I'll get rid of dust and so on, and Planck's data fits, Planck's curve rather, fits it, and it tells you the temperature in the background of the universe is a bit less than 3 Kelvin. 0 Kelvin is zero temperature, you cannot get to it, and the idea of negative absolute temperatures, no. So this is the afterglow of the Big Bang, and it works. Planck's thing really, really works. Okay, Einstein, also Nobel Prize. Einstein, in 1905, wrote 3 papers, and one of them was about the motion of atoms. It really convinced physicists that atoms existed. Chemists believed it already. Physicists were not so convinced. He also did special relativity, which is mc squared, and he also did a paper on the photoelectric effect. And Einstein's paper on the photoelectric effect was the second quantum paper ever. The first one was Planck's in 1900. Einstein's in 1905 was the second one. And he said, he thought a lot more about quantum theory than he had about relativity. So here we have the photoelectric effect. Some of you may have the photoelectric effect on your roofs because it's the basic idea of solar panels on your roof. Light hits this material and it releases electrons which produce currents and da-da-da. So Halbachs showed that metal exposed to ultraviolet light gets this positive charge. Didn't understand why. This was the first thing about the photoelectric effect, and in German the effect is actually often called the Halbachs effect. Halbachs, by the way, is the only person I think mentioned in this talk who didn't get a Nobel Prize. Despite the fact he discovered this thing, which, anyway. A little bit later, Thomson, Nobel Prize, showed that this corresponded to electron motion. So people had no idea what electrons were really. He was the person who showed that these seemed to be particles. Before that, you may remember from school the words cathode rays. It just means electron, but they had no idea what it was. Leonard, 1902, Nobel Prize, a couple of years later, so it's all getting fairly fast, showed that if you take 2 identical light bulbs and you shine it at your piece of metal, the electrons that come out have the same energy as if you have 1 light bulb at the same time. And so having more light doesn't make them more energetic. But if you change the frequency, so if you go from red to blue, they're showing it with ultraviolet and then higher ultraviolet frequencies, you get more energy. So it seems to depend on the frequency, but not on the intensity, which is a bit weird. You wouldn't expect that. And then Einstein said, okay, Planck was right. Light comes in quanta, and the energy is Planck's constant times the frequency. And if the electron needs a certain amount of energy to get out, it's just like, if you're thinking about getting something out of the Earth's atmosphere or throwing something upwards, you've got to give it a certain amount of energy so that it can achieve escape velocity. And the work function is just that. You've got to give it a certain amount of energy to get off, and then what's left will be the kinetic energy of the electrons. So Einstein has this idea, and he predicts this equation. You have, that's supposed to be F frequency. You have a higher frequency, you have more energy, and there's some minimal frequency, below which you get nothing. So straight line, really nice sort of thing that we've all done in school, drawn straight lines. And Millikan, Nobel Prize, Millikan, he wrote, I spent 10 years testing this equation in the top left. I mean, that is a very simple looking equation. He spent 10 years trying to prove it was wrong because he thought, no, this is not true. And in 1915, he was forced to admit the equation worked. So this is really radical. Einstein, about the same time, proposes Max Planck, about the same time, proposes Einstein for membership of the Prussian Academy of Sciences. And he writes he's done really good things in science, even if sometimes he's gone a bit too far, like with his work on the photoelectric effect. That's a bit too much. And then Einstein was given the Nobel Prize in 1921 for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Remember, by this stage, Einstein has special and general relativity under his belt. He's getting the Nobel Prize primarily for this. So, what's happening here is, again, jumping a bit now, but the idea is that everything in nature has got wave properties and particle-like properties. So, you know, this is sort of particle-like, but it can behave in a wave-like way. Something which is wave-like, like light, can also behave in a particle-like way. We talk about photons, sort of particles of light. So, particles, we have a rough idea what they are. Billiard balls, deer mats, not very good particles, but you get the idea. And they typically have a well-defined position and speed. So if you take this, it has a position, room, a speed, and the electron, Thomson got his Nobel Prize for showing that seems to be a particle. What about waves? Well, we've got water waves, and a little experiment we could easily do, take a dish of water and just sort of tap in with 2 fingers at different points and just see the little ripple effect you get. And that was the thing that convinced people in the first place that light is wave-like. And you get interference effects, and you can do this with the electron. So that's really interesting. So remember, with particles, this cat is still alive and well and has home when I left her. Particles can go through slits, and the cat particle here, Dora, to give her a name, comes through a slit between these 2 railings, and she only goes through 1 slit, and there's no interference pattern or anything like that. Okay. We will return to cats. So what's an interference pattern like? Just very briefly. So you've got these 2 waves, and if you add them together, and they are, technical word is out of phase, and that just means when you've got the top bit of one, you have the bottom bit of the other, and vice versa. Then when you put them together, they'll cancel each other. They'll just add to 0, so you don't get anything. And if they're in phase, top of the top, bottom of the bottom, when you put them together, you get a bigger wave. So that's the sort of thing that underlies interference effects. And as I say, bowl of water, 2 fingers, you can start to demonstrate them, or you can go and just look at the waves on the sea. So the double slit experiment, not using 2 fingers and bits of slits in water, can be done electronically, and you have something that sends in, say, electrons or photons. It's been done with both and more. And you have these 2 slits that come through. And if they're just particles, you would expect to get a clock here, say, a clock here, but you wouldn't expect to get an interference pattern. If they're waves, you're going to get these blue bits are supposed to be, let's say, peaks here coming out, and then where peaks and peaks come together, you get bright patches where peaks and pops come together. You're never going to find the electron or the photon, so you get dark patches. That was done, and strong evidence electrons behave like waves, you know, convincing evidence light behaves like waves as well. despite the fact that light and the photoelectric effect also behave like particles. So, okay, double slit experiment. Now, in the year 2000, those of us who are old enough may remember that there was all of this stuff, sort of things like the greatest Britain and the best of this and so on. So physicists, being just as silly as other people when it's not about differential equations, have this idea of a poll of the readers of Physics World. What was the most beautiful experiment in physics ever done? And I'm about to show you the results from the one that won. Okay? So the most beautiful experiment, according to ever in physics, according to the readers of Physics World, was a double slit experiment. Here you've got two slits. You've got a source that's sending electrons. They go through and it hits the screen, and then you have a dot there to show where it was. Now, that's fine, but the thing is, it's one at a time. So they send one electron through, hits the screen, and you get a dot. You can, I hope, see the dot there. And then what you do is you do this again and again, but only one particle at a time. So here we've got 3, and by pure chance, and I think I'm talking to an audience of people who've thrown enough dice to think, yeah, of course 3 things can randomly appear in a straight line. Why the hell not? Okay. So you've got these 3 dots. Right. The thing I really want to emphasize is that no stage is there more than one electron going through the system at once. And these dots are just recording where they landed. Okay? So, I've now got a video to show you, and I think the easiest thing is to go and just play the videos. Okay, so at this stage we've got 4 dots, and the straight line, got 5. And at this stage the straight line hypothesis is definitely broken down. So this is what happens. There is going to be some jumps, by the way, because otherwise we get really bored. There's going to be a grand total of 50,000 dots at the end. So at the moment, I hope you'll agree, it looks pretty random. One stage, but at one stage there's no more than one electron going through. And we're just, where it's hit, we just record that dot stays there. Again, it still looks pretty random, I would say. I wrote to Tom Mora, by the way, and who did the experiment, and he wrote back saying, I think seeing this video is essential to understand this experiment. Starting to see. So it's starting to look like there are areas where it's very likely for an individual electron to hit the screen. Areas where it's very unlikely for an individual electron to hit the screen. I think I will pause there. We're probably at about 45,000 dots. So, what's happening here? At any stage, you send one electron through, and somehow it is producing an interference pattern in that there are regions where no electron is likely to land, and there are regions where it's really likely electrons will land. And that is an electron interfering with itself. So the way you describe an electron in quantum theory is you have this wave function thing, and the wave function has values throughout space, and based upon those values, if it's big, I'm simplifying slightly, but if it's big, you know, you've got a good chance of finding it. And if it's 0, you ain't going to find it there. And this is what is happening here. So you think of the electron as a point particle, you know, as far as we know, incredibly tiny. But before you actually make the measurement, you have this wave function spread out in space. And that you calculate that, you can do the calculation, these things can be predicted, and it works. So one thing that's also really worth really weird, by the way, oops, that, is supposing so how can you produce an interference pattern then? Which of the two slits has it gone through? Well, you can't say which slit it's gone through. It could have gone through either, both, whatever, we don't know. But if you say, I'm going to put a little thing to measure if any charged particle goes through one of the slits, if you do that, the interference pattern disappears. So it is very, very weird. Okay. So the electrons are described by waves. Everything's described by waves. These waves are related to probability. They're not probability, but there's a relationship to it, which is a bit mathematical. The waves spread out through space. The electron can interfere with itself, and you can get things happening like that. Einstein hated this. And I don't think Einstein was religious, but he said God does not play with dice. Okay? Niels Bohr, whom who is a very philosophical physicist as well, also a Nobel Prize winner, said, "Stop telling God what to do." Somebody else that you've heard of to do with quantum mechanics is Schrödinger. I don't like it, and I'm sorry I had anything to do with it. Which I think is a bit ungrateful for somebody who, as you know, won a Nobel Prize. So, yeah, Schrödinger actually produced the equation, that he's one of 3 people in some sense, produced an equation which describes the wave. Okay, so they don't like it. This idea that, because it's all to do with what is reality. And if you're thinking that I'm going to explain to you what reality is, you are so wrong, because I don't know, and I find it very confusing, and I try not to think about it too much. So, what are the interpretations of quantum mechanics? One of them, the most popular one probably, but I will show you something at the end to show it's not that popular, is the Copenhagen interpretation. So, Copenhagen interpretation does what I was really just saying a moment ago. Your particle somehow gets from here to here. Which slit did it go through? No idea. That's not a question you can ask, and it's meaningless to ask it. And Anton Zeilinger, if you would like to read a book about recent quantum mechanical experiments, I would strongly recommend that you read his book, or that you just read about what he's done. He would be a very good person to read about. And as you know, of course, he got a Nobel Prize for his work. This is by far the most commonly taught one. He got a Nobel Prize as well. I'll come back to that later. The many worlds interpretation you've all heard of, and we all like them. I hope we all like the mirror universe in Star Trek. But the many worlds thing is everything happens and different universes are created. Now, think about it. 50,000 electrons are going through this double slit. So 50,000, they all could have gone that way or that way, and all the different combinations. That's quite a lot of universes created for one experiment, and there's quite a lot of things happening around us. So the number of universes out there is in no way small. So Occam's razor of going for the simplest solution, if you're going for that, you're happy with an awful lot of experiments. And then there is the one that people use in practice most of the time. Shut up and calculate it. And that's what it's called. Okay? So you just do the calculation, you get the result, and you say, I predicted that this molecule will have this color. I'm using the quantum chemical example from Gary, and yes, indeed, it does have that color, and you can predict it from quantum mechanics. So the question we have is, what on earth is reality? And Einstein hated it, Schrödinger hated it, and a lot of other people did as well. So I'm going to tell you a little bit more about that. Okay? But I've just tried so far to say a little bit about quantum mechanics is needed. Quantum mechanical results are widely used in fundamental science and technology. All seems to work, but it's very strange to interpret it. Nobody has a good, simple interpretation. Now, I know of people, I mean, Simon is really keen on Copenhagen. There's a guy called David Deutsch, who some of you may have heard of. He's written popular science books. He says, if you don't believe in the many worlds interpretation, you're stupid. And I think I'm not mistaking how to phrase it. I think he's far too strong now. Back to cats, hooray! Yay. So, this is my translation of Schrödinger's original description of Schrödinger's cat. You can construct a completely ludicrous idea. The cat is locked in a steel chamber together with an infernal machine. It's a Höllen machine, an L machine in the original German. Brackets, which you have to prevent the cat from having access to. I think he thought about this a bit too seriously.
Maybe he knew a bit more about cats.
Okay, so you have your idea, and you have a quantum source, so something radioactive, and it's fairly random. Will it now radiate? If a radioactive source, it doesn't radiate, bang, 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 an absolutely regular thing. It can do it now, it might be a little gap, it's all a bit random. It's all a bit quantum-y. And then that might or might not trigger a Geiger counter, and if it triggers, the bomb explodes and the cat is dead. And if it doesn't, the cat's alive, and when you open the thing, it's going to give me breakfast. And angry as well, yeah. And the thing is, you don't know until you open the chamber. And more to the point, and Schrödinger, when he set up the Schrödinger's cat idea, he's using this as a sort of reductio ad absurdum. He's saying, this is stupid, this cannot be. But what quantum mechanics says is nothing has happened until you open the chamber to look. It might be alive, it might be dead when you look, but before that, it is not the case that when you open it and look, you go, oh, it's alive, thank God for that. It's not the case that before that it was alive. You could have opened it and found it dead. You don't know. So Schrödinger hated it. This is ridiculous. This cannot be the case. So I'm just trying to give you an idea of how it is that people really, really find quantum mechanics strange and weird. So this is a quote from Einstein. The moon is there even if I am not looking at it. Einstein says, I believe the moon is there. It's not that I turn away. And of course, in reality, what you would always say is that the probability of turning around and seeing it not there is so close to zero as to be zero. But if you look at small scale things, what is their reality? And what does that mean about the reality of big things, really? Because we are made out of small things. Okay, so that's Schrödinger's cat. The EPR paradox. This is, EPR is Einstein, Podolsky, and Rosen. And actually, sorry, I lied to you at the beginning. Podolsky and Rosen didn't get the Nobel Prize, but Einstein did, so that would have to do. So they wrote a paper, and the paper is trying to say this quantum mechanics stuff is nonsense. It's not true, doesn't make sense. And I'm not talking about it the way they did the description, but this is the standard sort of description people would have nowadays. So you've got some sort of source, and there's a property called spin which tells you about how charged particles react in magnetic fields. Okay, we don't need to know anything about it except for an electron. If you measure its spin in a given direction, you either get up or down. And so we have a source and it emits two particles. For simplicity, let's just say it's an electron and an antimatter electron going away from each other. And if you, at some stage over here, this is just Alice and Bob, it's always Alice and Bob. You don't have any friends, they only know Alice. So let's say that Bob does the experiment first, he's impatient, and he measures spin up. Then what you know is that when Alice does her measurement, she's definitely going to get spin down. Now, quantum mechanics says, before you do the experiment, it is not the case that it has spin up and that has spin down, but you could have got either. And then you do the experiment here, and if you get spin up, that means that even if you've let these things go for hundreds of kilometers in both directions, you know immediately that one's got spin down. Now, you can't do anything with that information because you can't tell Alice because she's hundreds of kilometers away. You've got to send a signal at the speed of light and so on. But in principle, what's happening, this is what Einstein, Podolsky, and Rosen were trying to say is ridiculous. What's happening is, you know, you are saying something by doing that, the universe over there is changing. Okay? And as I say, it is not the case previously, according to quantum theory, that that was up and that was down. Okay? So, quantum mechanical theory says that you've changed something instantaneously a long way away. And this is sometimes referred to as spooky action at a distance. I think Einstein used to talk, for those who speak German, of quantum spook. Spooky. Okay. So, Einstein, Podolsky, Rosenberg, this is utterly unacceptable. This is not how the universe can be. It gets worse. So, Bell was a Scottish physicist, John Bell, and he took the EPR experiment and he made it a tiny bit more complicated. So if I'm going to say measure the spin upwards here, what he said, what would happen if, let's say he's Bob, what would happen if Alice measures it not upwards but in this angle? You know, what's her value? Quantum theory gives you a prediction, tells you what correlations there should be between this and that. And the classical theory of saying, well, it's definitely up and that one was definitely down, actually gives you a different result. So you can do experiments and see whether it goes with the quantum theory or the realist theory. And experiments, Alan Aspect, who, as you know, got a Nobel Prize, shared it with Seilinger. The experimental results agree with quantum theory. Okay. So, at this stage, we're in a situation where the idea that out of this, it comes out and it's definitely up and that one's definitely down, seems to be rejected by experiment. It's not possible. So if you want to look at Bell's inequality or aspect experiment, you will find out more about that. So at that stage, I think I've said enough about weirdness. And let's just say a little tiny bit about quantum computing, which we've all heard about. So quantum computing is a quantum state. You have, say, 10 electrons, and then they could all have spin up, or they could all have spin down, or there could be some mixtures. And you have 1,024 possibilities. So actually, that's just a bit of fun. With your fingers, you can count from 0 to 1,023. Just with your fingers. 1, 2, 1, 2, 3, 4, 5, etc. You can do it. So if your quantum state, according to quantum theory, is in all of these possibilities, if you can work out a clever quantum algorithm, and Peter Shaw is somebody who works on that, then you can use in principle quantum algorithms to solve hard problems. And I remember being at a summer school about quantum computing, and the guy who was giving a series of lectures, a guy from Oxford, said, it'd be really lovely if the quantum weirdness all disappeared if we built a bigger quantum computer and we just had boring classical mechanics appear. But nobody's been able to build really a big quantum computer yet. It's very, very difficult to build these things. They tend to be built very cold. So that's quantum computing. Can it be done? So can we learn things from quantum theory? Well, yes. I mean, you can look at the solar spectrum, the light from it. You have these lines in the spectrum. Quantum mechanics lets you work out which lines correspond to which elements, etc. Gary, the sort of thing he was talking about earlier. You can look at the light from the atmosphere of a planet, and you can look in the spectrum and see lines that correspond in principle to something like methane, and go, that doesn't seem very stable unless something's making it. So these things are very, very interesting in principle. What causes the spectrum? How is it? We've never landed a probe on the sun. Good luck to someone trying to do it. But how is it that we know what share of the mass, what share of the number of atoms is made up out of these elements? It's because we look at the light coming away, and we can work it out. Okay. So I haven't got any conclusions. But I have a quiz. Now, the good news is this is not a quiz for you. I'm going to tell you about the results of a quiz that was published in Nature. So, one thing that I skipped over, quantum mechanics, no, not quantum mechanics. Quantum theory started about 125 years ago with Max Planck. To get from that to what is called quantum mechanics took about 25 years. So this year is 100 years of quantum mechanics. So of course, there's a conference organized where people could go to this conference, experts about quantum mechanics, and Nature, the famous scientific journal, asked about 500 experts on quantum mechanics earlier this year what they thought. So this is purely what you like, but what did they think quantum mechanics might be explained by? And actually, they had over 1,000 people that replied to it. Sorry. Anyway, here we go. Copenhagen interpretation, about a third went for it. But you can see dark blue confident. Early confidence a bit more. Something, it's all to do with information. Reality is somehow to do with information. And Seilinger is somewhere, I think, between these two. And he actually made a statement about this thing, saying what he thought. And Alan Aspect, who also got the Nobel Prize for quantum theory experiments at the same time, they shared it. He said, no, I disagree with what you're saying. So people don't know. Many worlds, significantly less. And then there's other types of things that people don't know. So, that is almost the end of the talk. I should just say perhaps a couple of words about the Nobel Prize for Physics this year. So the Nobel Prize for Physics this year was awarded for people doing something called tunneling, which you may have heard of. And I was going to ask my glamorous assistant, Gary, he would help me demonstrate what tunneling is. Get over here to avoid hurting other people, just carry. So, in classical mechanics, if you give something enough energy, it will go to a particular height. So I'm going to give this enough energy, I hope, to get over Gary. So that's how it is thank you very much. And in classical mechanics, if I don't give it enough energy, it's not going to get over Gary. So that was really, really major. Now what happens with quantum theory is I don't give it much energy, and it can appear on the other side of Gary. Or I give it lots of energy and it still bounces back off Gary. You know, despite the fact I give it loads of energy, it can bounce back. Both things can happen. And you know, the picture, if you remember, of IBM, the letters, that was done using tunneling. So it is definitely seen all the time in use. Round of applause for Gary, please. So what happened this year? Well, actually, you know, what happened, oh gosh, I'm going to say 40 odd years ago, but there's errors, I've forgotten when it was. These three people, they looked at something called superconductivity. So superconductivity is you have some metal, some wires, whatever, and you really cool it down. You get to very close to zero. And then you can get no resistance if you set it up right in a circuit. So the current just goes without a resistance. Now, if you think about it, resistance occurs like, you know, when you're walking down the corridor and you're banging into people a bit. So the electrons are banging into people a bit. So if you have superconductivity, basically Armadacon has, in the corridor, turned you all into robots marching together in perfect phase. Okay, so that's what happened with the electrons in the superconducting circuit. They're behaving like one. And these people who got the Nobel this year, they showed that tunneling can happen with superconducting circuits. There's a large number, something like 1 million electrons, can behave as one and do things that are forbidden by classical physics. And this is something which in principle is really important for things like quantum computing and so on. But quantum computing, I think, is still a long way from, you know, really solving big problems. You know, it's still very much in early days. After all, think about it. If you want your laptop to be cooled down to minus 272 degrees C. So, all tricky. So, with that, I think I'm finished, but I ought to say thank you to my collaborators, neither of whom were harmed in the making of this talk. Thank you very much.